Okay, welcome everyone to my continuation of what is algebra. Today, maybe my favorite theorem from algebra, or at least from some kind of a classical course on algebra, the fundamental theorem of Galois theory. So there's a reason why this is called the fundamental theorem. It's not the fundamental theorem of algebra, that's about roots of polynomials in the complex field. Well, this is also about roots of polynomials, but in some different way, in a more combinatorial way. And it's just kind of the most important theorem, and in the class in Galois theory for sure, and maybe also in the classical class on algebra. And it's very surprising in my opinion. It basically says that studying roots of polynomials is a matter of combinatorics, which is a very surprising statement, because if you first try to solve polynomials equations of high degree, or you would feed them in a machine or whatever, so the machine most of the time would just try to find numerical solutions. So certainly trying to solve polynomial equations, and I'm talking about polynomial equations with, let's say, rational coefficients here, the computer would try numerical methods, and it's definitely a part of analysis or numerical analysis or something like that. And Galois theory wants to say, no, not quite, or not. It's not just a matter of numerical analysis, but it's also part of combinatorics. And by combinatorics, I really mean group theory here, or to be completely specific, finite group theory. Throughout, I kind of would like to ignore the infinite case. The infinite case exists, okay, sure, but I'm mostly doing finite examples, and I'm caring about the finite cases. And finite group theory and combinatorics are very, very similar. So I will show you some calculations here and there, and I stole them from a very nice site, which is linked in the description, which is called groupprops. So pick your favorites group of small order, and it will list certain properties of that group, whatever, a number of conjugacy classes of subgroups, something like that. And how does it do, how is it done? Well, you feed the problem into a machine, and the machine just calculates and gives you the answer. And it works up to really a reasonable size of the group. Of course, at one point that breaks down, but for some groups, they also then list formulas for Sn for certain types of Sn. Some, but most problems in group theory, you just can't list them by formulas. You just, it's a brute force combinatorial computation. But again, this is not really bad, because, well, it's combinatorics and the computer can do it. And for all examples you probably ever care about, the computer can do it anyway. So I don't know. I've never really met a group of order 1,000,004 in practice. Um, I, I can't even think about many groups of order 1,000,004, except some trivial examples like Z modulo 1,000,004. Anyway, so Galois theory, or this fundamental theorem of Galois theory, now relates roots of polynomials, a matter of numerical analysis, if you want, as I said, to combinatorics, which is pretty amazing. And it's even better. So it's also it's a two-way street, right? It's really a win-win situation. It's a win-win situation for people who like roots, and also for those who like groups or combinatorics. So let's get started with an example, something easy. And in my opinion, and this is how I will, well, how this video works, is the group theoretical side is a combinatorial side, is the easy side. The root theoretical side is a complicated side. Okay, it's root theoretical formulated in terms of fields, but it's still way more complicated in some sense than the other side. And Galois, the fundamental theorem, will tell you that they are the same up to a certain point. So since I personally think the group theoretical side is easier, let's start with a group example. S3 and its subgroup lattice. So here's the subgroup lattice of S3. So how do we read that? Well, we have S3 certainly at the top, which is, well, a subgroup of S3, a boring one. Here's another boring one. It's certainly at the bottom, the trivial group. And we want to look at things that are in between. And I claim, or let me say it again, I got this actually from the link in the description from this group prop web page. It's a really nice web page. Okay, in this case, I could have calculated this myself. It's S3, it has 6 elements. But anyway, I'm lazy. So I got it from this nice page. And it tells me, or my computation would tell me, that there are 4 non-trivial subgroups. And by 4 non-trivial subgroups, I mean really if you care about the elements in that subgroup, in those subgroups. So you have a Z-mod copy of Z-mod 3. Some people would like to call this A3, the alternating group in 3 symbols. And you have 3 copies of Z-mod 2. Okay, very good. So you have 6 subgroups, and what kind of really matters is that you have 4 up to conjugacy. And conjugacy is, is illustrated here in my example by this left-right little edge. So all of these are actually conjugate. And yeah, they have different elements if you really list them in terms of elements, but we already learned that in some sense that doesn't matter. It's just renaming of things. So the right notion of equivalence here is up to conjugacy, and actually all of them are conjugate. The other one has no, well, it's its own conjugacy class. There is no other copy of Z-mod 3, so, well, it's conjugate to itself. So anyway, depending how you count, it's either 6 or 4, and I would promote counting as 4. You can actually do that in quite general, again, links in the description, but here it's 6 and 4. And how do you read this? Well, I have those red edges. Here's 1 and here are 3. And this means it's an index 2 extension. So the corresponding notion on the side of the polynomials will be degree, but here it's called index for groups. Anyway, and then I have a purple one, which goes this way and this way, which is, well, an index 3. And note that they are built such that you always have 2 times 3, which actually is this index 6 of S3 over 1, because, well, S3 has 6 elements. That's all I said here. Yeah, and the point is, well, you can see they have this bubble of, this little bubble here. And this tells you that those guys are not, they are not normal, because their conjugacy class is not trivial. In contrast, A3 is this normal one, right? So this whole diagram tells you all of those 4 bullet points. It tells you the number of subgroups. It tells you the conjugacy classes. It tells you the indices, and it tells you which groups are normal and which are not normal. And the main observation that kind of started this whole thing is that, well, I'm not 100% sure, right? I mean, we probably will never know, but kind of people played around with, people like Galois played around with this picture and realized that there's something going on the side of the roots as well. So let's have a look at the root picture, or more modernly formulated at the, well, field extension picture. And you do the same game, basically, and the field extension I would like to study is this one. It's zeta, and zeta is the third root of unity, this non-trivial one. And then I have this third root of 2. And that's a degree 6 field extension. And here's its subgroup, or its subfield lattice, and it looks exactly the same, right? It looks exactly the same. Yes, this little bubble here, I will explain the bubble in a second, of 3 field extensions. You have the one sitting alone. The only thing that kind of happens is, in contrast to the other one, is everything is kind of upside down. So here's a red edge, as you can see, and a purple edge, meaning now the degree of the extension. And here it was exactly the opposite. It was a purple edge and a red edge. Same for all the other edges. So it's the same picture upside down. And this will be crucial, of course, in the Galois correspondence in the end. So it's really the same, and all notions are reflected, but everything is kind of upside down. Anyway, the calculations are now the same. You have 6 subfields, you had 6 subgroups before, right? And depending how you count, you have 4. And in this case, the right notion would be to have automorphisms of your field. So up to kind of permuting things using automorphisms of your field, there are only 4. And it's the same story. You have 3 sitting in the same bubble, and you have 1 sitting alone. And yeah, as I said, you can read off the degrees, but they turn the other way around. Okay, that was the same here. And now what about the bubble and the normal? Well, it's the same story. If you have a non-trivial bubble, then those things are not Galois. Oh, the notion was the Galois extension. They're not Galois extensions over the small one, over Q. And if you have something sitting in its own bubble, then it's actually Galois. Right? It's a Galois extension. Really, really exactly the same picture. Twice the same picture, the only difference upside down, right? And that's pretty awesome, isn't it? I mean, if this was true in general, and of course it is, spoiler alert, if this would be true in general, then this would be awesome. That would be relate roots to subgroups and other structures in combinatorics, like lattices and so on, and conjugacy classes and so on. So this would be pretty awesome. Let me give you another small example, which is a little bit easier because it's a little bit smaller. It is not as nice as this one in the sense that if you understand this example, I'm pretty sure you understand almost everything about, well, at least basic Galois theory. Of course, you can push Galois theory as far as you want, basically. It's still an active field of research in some sense. Anyway, I'm waffling. So let me do another example. And again, so here's the easy one, the green one, and here's the hard one, the red one. And I really want to compare them now. So I'm claiming I want, well, what I'm interested in is the subgroup lattice of the Klein foregroup Z2 cross Z2. And this is almost trivial. Because, I mean, Z2 cross Z2 has those four elements, just written as tuples, with addition, with the obvious Z mod 2 addition, component-wise. So to write down the green one is, it's really easy. You can just do it. Maybe it's even clear to you right now. I mean, it's really, really simple. To write down the red one, so maybe I should put this actually in green. So let me put this in green. Put this in green. To write down the red one is not completely trivial. One note first, I decided to turn the red one upside down to make it more clear which one corresponds to which, because this was our observation, right? So I turned just the picture upside down. So this one under Galois correspondence will correspond to this one, and so on, right? Anyway, we don't have Galois correspondence yet. I just wanted to mention that I turned it upside down, which of course is just convention anyway. So I claim this is a subfield structure of Q adjoint root of 2 and Q adjoint root of 3. And this is not so easy to see. I mean, you could guess that those are the three subfields, but certainly that there are no other subfields is not quite obvious to me. And there are no other subfields. In particular, you can use the Galois correspondence to see that there are no other subfields, but it's certainly not completely obvious. But the way to prove it is, or the way you would like to do it is we would like to write down the Galois group, which is just those automorphisms, and you would check that they are spanned by two automorphisms, exchanging the sign either in front of the square root of 3 or the square root of 2. And then you look at the fixed fields, which is this one, and the fixed field of the product, because now you have two signs, one in front of square root of 2 and one in front of square root of 3. So the only thing that is fixed now is the product of them, which is square root of 6, which is this middle guy here. And then you need to convince yourself that this actually is everything, and this is how the picture fits together. So those are the subfields of this one, given by being fixed fields under certain automorphisms of your field. And again, I don't think the right-hand side is completely obvious, while the left-hand side is much, much easier. It's really much, much easier. I will come back to the much, much easier on the group theoretical side in a second, but let's just look at the Galois correspondence now. It's exactly what you would hope would be true. So if I would do those two examples, and it takes a really, really big amount of brilliance to just do that, like Galois and other people about 150 years ago. Anyway, if I would calculate this example and this example, then I might come up with the following conjecture. And it turns out that the conjecture would be true. So let's say you have a Galois extension over K by L, and the Galois group is always the automorphisms, where the second entry, so automorphisms of the first entry and the second entry is what you want to be fixed. That's the Galois group. And then the statement is as follows. So A is a little bit boring, but not completely obvious. So then L is not just Galois over K, but it's Galois over all subfields of K. And my subfields are always Z in this notation. Okay, anyway. So that's what you need to even make sense of what follows. Kind of ignore it. You shouldn't ignore it, of course, because otherwise the rest would be bullshit. but the main statement is certainly the Galois correspondence. So let's focus on that. So there are two inverse bijections, which are upside down bijections in the sense of inclusion. I will come back to that in a second. But as a bijection between the subfields, these, it's here and here, and the subgroups of the Galois group, which is here and here, given by either sending a subfield to its Galois extension, now the one L over Z, not L over K, or invert, the inverse is to send a subgroup to the fixed field. So that's what you do. And that's a bijection. So whatever side you would prefer, let's say you're a big fan of the red side, like me, then you would use the red side to describe the green side. The only thing you should note is, or the statement is stronger, it goes on. It's also order inclusion preserving, not quite, it's reversing. So if you have a bigger field, you get a smaller Galois group. Bigger field, smaller Galois group. Smaller subgroup, bigger field. Smaller subgroup, bigger field. You can say something about the order, which was this game I played here. So 3, 3, 2, 2, 2, 2, 3, 3. That was the order thing. And here is written down, order and index. And the last one that I was telling you about in my examples is you can check whether something is Galois by checking on the other side whether something is a normal subgroup, right? So that's what I did here. So using those bubbles. And it's secretly also here because everything here is its own bubble. Okay, so you have three different copies, three non-conjugate copies of Z mod 2 sitting in the client 4 group. And how can you see that? Well, client 4 group is in the building group, so conjugacy classes are always of size 1. So building groups are pretty simple. Conjugacy classes are always of size 1. Anyway, so this is the main theorem, the Galois correspondence from subfields to subgroups and back, right? Subfields to subgroups and back with some nice additional properties like Galois is reflected in normal on the other side. Inclusions are basically preserved, just turn your head, they're reversed, and so on. Really amazing. In a second, I show you an example how to really use that in practice. But let me just mention here briefly that actually the Galois correspondence also works for non-Galois extensions. It's just a little bit different. You don't have a bijection, but you still have something. You have surjection and injection. Surjection and injection. I hope I got the directions correct. Anyway, so let me finish with an example, with a homework example. And the picture, I stole from this nice page groupprops in the description, link in the description. Namely S4 versus explicit calculations. Here, in this case, you might say, okay, I could have done that on the field theoretical side. It's not so bad. And subgroups of S3, I'm not sure whether this is really worse. I say it's subgroups or better or worse. I say subgroups of S3 is still better than this picture, but it's not completely obvious. But if you look at subgroups of S4 and my homework, roots of this polynomial here, we'll come back to that in a second. So this is the root theoretical, the field theoretical one. On the other side, which I'm not showing you, it's a homework to do that. Good luck. Link to some discussions how to do that is actually in the description. But anyway, you might say now, okay, this diagram looks crazy. So let me explain how to read this diagram. So it's the same as before. S4 is at the top, C1, which is just a cyclic group in one element, which is just a trivial group on the bottom, and you have a certain subgroup lattice. And now they actually did it a little bit nicer. They ordered it by degree, by index, right? But secretly there is no really a height. But anyway, so here's my A4. That was Z mod 3 before. And it sits in its own conjugacy class. And you can see this because there's this little gray bubble outside, which means there's the little gray bubbles are basically conjugacy classes. So here's one, for example. Here's S3, and so on. And the red dots are different copies. So S3 sits in 4 different copies in S4. That's what it's saying here. The black dots are the copies, and the gray circles, or the gray whatever it is, are basically the conjugacy classes. Not quite, because here, for example, for this one, so you need to take the spacing in this picture into account. So here I just mark them. So here are the conjugacy classes. This one here, that's a client for group. It exists in 2 conjugacy classes and in 4 copies. That's how you read this diagram. And you list this this lattice of subgroups, which looks, I agree, it looks crazy. It looks, well, it's not so bad, but it looks reasonably complicated. And it will take you a while to do that by hand. For a computer, this is, of course, easy, but it will take you a while to do that by hand. So you might wonder, why on earth I'm always saying that this side is so much easier. Well, first of all, as I said, you just ask a machine to do it, and the machine does it in, well, this is S4. So in a few seconds, probably even faster. I'm still running everything on a very, very slow machine. But anyway, so this is easy. If you just look at the roots of this crazy polynomial here, and I did that using Mathematica. So Mathematica, you can use solve to do that. And Mathematica doesn't really know what to do with that. It gives you numerical solutions. If you force Mathematica to give you explicit solutions, well, let's have a look. So here's Mathematica. Here's the very same equation. And solve just solves it. And this forces Mathematica to use really expressions in terms of the standard operations of arithmetic, so addition, subtraction, multiplication, and division, and algebra, which are also roots. And these are the 4 roots in terms of root theoretical expressions. And I don't know how you feel. They look pretty weird. They look pretty crazy. And I also use the simplify command to make them as, so the Mathematica thinks these are the simplest possible expressions, basically, that's what Mathematica thinks, of those roots. I don't know, looks pretty crazy to me. In particular, it looks much crazier than this picture, which is pretty harmless compared to the roots of this polynomial down here. And now it's not just about the roots, you would need to calculate subfields of those things. I mean, good luck trying to do that. I would rather recommend to use, of course you can, because it's a one-to-one correspondence. There's some equivalence going on. Of course you can. But I would rather like to stay on the picture of the subgroups and the combinatorics, basically. Anyway, I'm already starting waffling, so let me summarize. So the Galois correspondence is a very nice correspondence between something combinatorial, subgroups, and something more, whatever, numerical, roots of polynomials, or in algebraic terms, field extensions. And it's really this one-to-one correspondence which turns everything upside down. And it's the most important theorem in Galois theory, and there will be a lot of applications of that theorem just in algebra itself. Anyway, I hope you enjoyed the video, and I also hope to see you next time.